Okay, let's get started. Today, we will look at several more format string vulnerability examples. And Thursday, we'll also talk about format string. And last Thursday, we talked about how to use format string vulnerability to arbitrarily read the memory space. And these two sessions, we will talk about how to exploit that to write to some memory location and get control of the computer. So the first example is from format string vulnerability to buffer overflow. So in this example, we have format string vulnerability and buffer overflow vulnerability. And but you cannot directly buffer overflow. That's what we learned in the first half of the semester. However, the format string vulnerability will help us to do that. So main function only calls vol tool here. Vol tool has two local variables at SQL level, 100 bytes each. Then there's a fget to get input from std_in, and it's only getting 99 bytes. And fget will append under of 9 a new line there. So this will make it 100 bytes of input, or maybe 101. But definitely it's not going to overflow a lot. Even if there's 101, it will overflow 1 byte of buffer 1, right? Because you are writing to buffer 2, not writing to buffer 1. So there is no way you can overflow the return address or save the EDP on stack. Also, this executable doesn't have canary, and non-executable stack is disabled, which means if you are able to inject the shellcode there, you will be able to execute the shellcode. And also there is no stack canary, make buffer overflow easier here. Now after that, so this time, no serious buffer overflow. However, the next line, sprintf, will print whatever in buffer 2 to buffer 1. And buffer 2, where do you get buffer 2? Buffer 2 is user input, can be anything. Buffer 1 is on stack 100 bytes. So buffer 2 here is actually a format string. Okay. Buffer 2 is a format string, which means you can put arbitrary format string there. You can put a lot of %n there, %x there, whatever you want to do. And that will be expanded in buffer 1, which means a short string here may become a bigger one in buffer 1. Does that make sense? You have a percentage 100d, that is percentage 100 is 3 characters, e that's 5 characters, 5 bytes in total. That 100% d, when you print f to buffer 1, you get 100 bytes, right? So this is like a magnifier here from 5 bytes to 100 bytes or even more. So now this printf, this format string vulnerability actually give us a tool to buffer overflow the buffer 1. And because of that, we will be able to overwrite the return address or save the EDP or whatever. Right? So that's the idea of how do we hack this one. So the prototype of printf is the first one is the destination of the buffer, and the second one is the format string. As you can see, we can have many parameters after that. So the important one is the second one, the format string. But the format string are not necessarily the first parameter in this class of functions. Many of those functions, the format string are the second one or even the third one. S3 printf is even the third one. Okay. So this is a binary of this program. Let's take a look at this. So because we are doing buffer overflow, we want to figure out how much bytes we want to overflow here. This is a Volvo, and the first instruction is just NBR. Then we have push EVP, move ESP to EVP, push EVP, subtract something from the ESP, and it's actually big here. It's E4. After that, we have underscore get PC thunk dot bx. So we talked about this before. So this is related to the position independent code, right? We're basically getting the current PC value, which is program counter value, into BX, into the register BX. So the reason for this is to do address space layout randomization. The code has to be placed at many different places. However, some of the code instructions, they were referenced, they use relative reference to other resources. So they need to know the exact address of where those resources are. And by doing that, they first to figure out where its own its instruction is at. So after we're getting that address, we add an offset there, and that offset is some resources we have. Then we move that address, the value to EAX here. Then we dereference that EAX. Then we subtract 4 from ESP again. Then push EAX. So you can see here, we are making the first function called fgets. It's our first function called fgets. Before fgets, we push EAX, then we push 63, and also push another EAX. So the first EAX is actually what? The buffer's address. And from here, you can say the buffer's address is EVP minus E0. The second 63 is at 99. And the third one is the format string. Okay. So the format string obviously is not on stack. That's a hard-coded. No, not a format string. That's it is a format. No, that's STD. Sorry, that's a STD. So this EAX is actually STD in the fire pointer of the fire descriptor 0. In fgets, we're not using fire descriptor. Fire descriptor 0 is standard input. And in this case, we're not using number 0. We're using a pointer, the equivalent pointer for that. So after that, balance the stack and turn to ESP, subtract ESP8 again. Then we have the second function call here, which is sprintf. And sprintf, we have buffer 1 and buffer 2. Both of them are on stack. So the first one is the destination, buffer 1, and its location is 6C. The second one is at E0. So 6C obviously is smaller than E0. So if we draw this, the stack will look like this. Return address, save the EVP. From buffer 1 to save the EVP, we have 6C, which is 108 bytes. From buffer 2 to save EVP, we have E0, which is 208 bytes, which means compiler gave us exactly 100 bytes for buffer 2. Buffer 1 actually will have 108 bytes, and we do not have stack arrays in between. Then it's just a standard function exit here. So let's first verify if the program we have on the platform has the exact code, the binary code, because we recompiled it recently. If there are some changes, will be some minor changes. 3. Let's verify if the values are so the values are the same, B0, 6, 6. So then how do we hack this one? Relatively easy, because it's buffer overflow, what we did before. We put a piece of share code on a stack, right? And we use the format string to override the return address. Let's try that. This is our share code. Let's put a unique and offset there. So we export S code. Let's verify this. The size of the offset 1,500 bytes. Then we have this share code. Which share code is this? This is just print flat share code we developed before. So put it there. Variable 32 S code. This address. Then share code is already there. The input is std. So if we do this, are we going to trigger a buffer overflow? So no matter how many bytes we put here, it will not trigger a buffer overflow, right? Because we're only reading 99 bytes from here, right? But even if you put 1,000 bytes here, the program is not going to read that. Yeah. So when you put more, it will not trigger a buffer overflow. However, if we put percentage, let's say percentage D, let's put 1,000 percentage D there. This is just one format string specifier, and that will put those 6 bytes into buffer 2, and that 6 bytes will be expanded to 1,000 bytes to buffer 1. So that will trigger the buffer overflow here. Right? If we do this, we get a segmentation fault. Okay. But that's not our goal. Our goal is not to get a segmentation fault. Our goal is to get a flag. So what do you think? What is the exploit we're going to use? For the address of the environment variable that is first argument, that is on the side, kind of get the address of that. Why do we need to put that in the first? That we can add that as a data movie. Yes, but why do we need to put it at the beginning of that buffer? Input it anyway. You need to use that to override the return address, right? But in this case, you first, yeah. The address. Okay. Pressing the and override. Does that work?
Right.
You go first, yeah.
I think my thought probably naive. I would be inclined to do something like %108 the address.
Okay. Yes. But actually, I think your approach will be easier. Your approach will be harder here because you don't know that address, right? Because that address is on stack, it's dynamic. In this case, you don't know that address. So you do have a power here is percentage n, can arbitrarily write to any place, but the problem is you don't know where that is. In this case, we know the relative address from the start of buffer 1 to the address, so we will be able to calculate that. Okay. So let's go back here. Oh, wait. So we have, yeah, this one. So what we can do is we can do a percentage 108. But 108 is not enough, right? Because we also need to override
right.
and save the.
Yep.
Yeah. So we just do a 104 bytes of that, 112 B, right? So the B doesn't really matter. You can use X, you can use whatever. Okay. So this is just to fill the buffer. Then after that, you will have the address of that share code. Okay, then 4 bytes. Yeah. And this one, we're looking for something on the stack. We use as a parameter, but it's only looking for an integer. So you don't need to give anything, actually. We're using some arbitrary garbage on stack to fill this. So the exploit will be very simple. Just do this. Let's try. So here we already put the share code on stack. So we need to, what's the, we need to do this. Um, this. I do. Percentage 112B. So we have that address. Okay. We have a huge doc set, so we will choose something bigger. So B8, B8, maybe I just use the SQL. That's two should be okay, right? Or that's too big. That's too probably too big. B8. Oh yeah, that's too big. B8, maybe B8 would be fine. You can B8. Just try mine first. Okay. So that will be our exploit. Our exploit is only like this. So we pipe this exploit into this. Let's see if we get it. Yeah, we get it, right? So let's try B8. Eight. Even B8 actually give this B7. B7 doesn't work. 8 works. So we put the environment variable. We put the share code environment variable. Obviously, you don't have it. You don't have to put it there. You can put it anywhere. The buffer in this case is huge. Right? You can write as many bytes as you want. So you can actually write the share code into buffer 1 after you overwrite the return address. But in this case, you need to figure out the address. You still need to figure out the address. This one should work. Let's try this as well. So first I unset S code. So right now we do not have the share code. but we do not have this S code environment variable now. Yeah, we don't have it. So it's not on the stack. Now we have to put the share code in our address space. So let's see. This. Here we have this. Before that, we should have our format string, percentage 112p, then those address. Oh, the address here will be a little bit tricky. We don't actually know the address. After that, we have, we'll make it even bigger. So the address, let's say, so the address we used before was B8 something, right? And that is the address of, where was that? That's the environment, but we're very high. Yeah, so we should use the address much smaller. Okay, then let's try maybe B0. This one doesn't really matter, right? So we try this. Maybe too much. Let's try from D7. Then we type this into this. Oh, file name. So
So could it be that there's two money dollar signs at the very beginning?
So we don't really need the dollar sign, that's for sure. Yeah, we don't need that. Yeah. So segmentation forward, let's try smaller. Because our offset is huge. So are we using D8 before? 8, huh? Also possible it will go up. 9 plus D2. Let's go even lower. 0. Great. Okay, let me cheat a little bit. Let's debug this. Here. Oh, yes. Okay, here's D6 something. About this, so it'll be lower than this. We already tried B something, so this part is correct, right? 112 B, FF. This part is correct. We didn't touch the share code. That should be correct as well. Let me make this even bigger. And we start with B6. Start from there. But we're getting something. That because this one is too big. I think that's because the whole thing is too big. B6. 4.
I got a question about this approach. Aren't we only able to input 100 bytes to buffer 1 or to buffer 2?
Oh, yes. We can only include 100 bytes in buffer 1. Yeah, but in this case, this is smaller than 100. Oh, the offset is huge here.
Yeah.
Oh, yeah, this one is huge. Okay, yeah, you're right. So we cannot have a huge offset like that. So the offset, I mean, 50, 60 bytes at most. So we can say, let's say this is our output. Then we do a word count. Say, oh, that's even too big. That's 117.
We get it minus to 43 bytes.
Yeah, 43. Then to be safe, let's just do 40. Yeah, the 40 maybe. Then we go back here. So the offset can only be 40 bytes. For that, we'll make it a little like 3, have like 6 something. Right? 6, 7C. That's, oh, we're going to try this many times. Maybe we want to 40 bytes. So we cannot even change it here. We have to change this part. Yeah. So we probably need a script to keep trying to eventually get there. Okay, I think we can skip that. But it's obviously doable. We just need to try many times. So that is the first example. In this example, we're still exploiting a buffer overflow, which is a sequential override of buffer 1 there. So now we're going to do something different. We're going to overwrite global variables. We're going to overwrite some arbitrary address. In this case, this is our vulnerable program. We are going to try 2 different ways to hack this program. And the first way is to override the global variable. The second way is to override the return address on stack. But going back to what you say there, the tricky thing here is you need to figure out where is the address of the return address on stack. So I actually printed out for you in this challenge. So this piece of code here is to print out the runtime address of the return address of the stack frame of vol. In the first approach, which we override the auth global variable, we don't really need that. The second approach, we already do that. So let's look at the first approach. We have a global variable auth initialized to 0. We have a local buffer for the temp buffer, 512 bytes. So after that, we have fget, get input from std in. And here you know that this fget is not going to override temp buffer, okay? Because we're only reading 5 10 bytes, appending to, that's just enough for this. However, there is a printf using whatever your input is of the full master. But this is f print. This is not the s print, which will put the output in a buffer. This one will print out in the terminal, right? Okay, so this one, this printf will not overflow the stack of this program. What is the second approach again? Oh yeah, this one is not going to overflow that. So then in the main function calls powerful, then if auth, then print flat. So you need to change the auth value to a positive number. That's it. So how do we do this?
Repeat many times and then we get the redirection equal to 0, that means that is the oscillating.
Dereference to 0.
We just give the format string as percentage, like my
Which format string specifically you're thinking about?
percentage.
Isn't it S?
XX.
XX? Okay.
So in that case, we will get the dereferences of all the variables.
Okay.
I can see a 0 somewhere, so that should be the order.
You see a 0 there? Which one is it? You think the 0 in the stack is this one?
Yeah.
Or this one?
And it will be
Which one? So when you put percentage X, percentage D, whatever here, you are reading the parameters on stack, right? So you will be able to see this one, but where you'll be able to see this one? Yes, that will be at the dot data section, which is for initialized data. Usually it has a smaller address than stack. So no matter how many percentage X you put there, you actually do not get this one. You only get this one. Yes.
The data is lower, right?
Yeah. Data is lower. That's it.
You can only read it.
This is somebody saying, okay, so it's first of all, there's a local variable called stack. It's initialized to 0. Then the instruction here, there's just one instruction. This one is the AT&T syntax, not Intel syntax, which means the destination is the second one instead of the first one. The destination here is %0, which means the first variable here in this case. We're moving the value of EBP to there. Okay, so at this point, the value of EBP, what does EBP points to? EBP points to saved EBP, right? So we are getting the value of EBP to the local variable stack here. And the reason I want to do this is I want to print out the address of the return address on stack for you. So I plus 4 on that value, because that value is saved EBP's address, plus 4, then print it off. That's it. So in this case, so which format string specifier we should use to overwrite, to write something? Yes, we use %n. So what do we need for that %n? The what? Yeah, but that's not our input. That is what percentage will overwrite the value, the content will overwrite. So percentage D will look for an integer, right? Percentage X will also look for integer. What does percentage N look for the parameter? Yes, an address. So which address we should give here? Yes, so how do we get that address? That's a global variable, right? So it's easy to get the address. Yeah, with the problem, we just use an N, we can get the address. Try that. Format string label 5. Let's say maybe we do an N. We have the address. Regret. Oh. Okay, we have our address here. As you can see, B, what is B? I don't remember what B is, but this looks like a correct address, right? So this could be the correct address. So then let's try that. The what? So where is our input? STD. I_2. Bring. So what do we put at the beginning of this? We put the address here, remember? So this one, we actually tried this before. So we are so let's go back to the recode. So our format string actually goes to conf buffer, right? Our format string goes there. So the stack will look like, we're talking about a stack of waffle here. We have return address. We have saved the EDP. Now after that, we will have the local variable stack, which is 0. So after that, we will have the buffer, which can be 512 bytes, right? Okay. And we are putting the format string in this part. Okay. We can put whatever string in this part. And then we will call printf. And the printf stack will be somewhere here. The printf stack will be somewhere here. And printf stack will look similar to this. It will have a return address, save the EVP, its own local variables we do not care about. So all of this we don't care about. What we care about is its first parameter will be the address of the format string. It will be the address of the format string. And it will be here, right? It actually only takes one, it only used one parameter. But depending on the format string's content, you may interpret that it has many parameters. Okay. So if you put a %x here, this %x will map to the second variable, right? If you put another %x, it will map here. Eventually, you want a %n here, which can map to some place you can control. It can be the place you can control. It can be somewhere in environment variable, okay? And there you don't even need you can have a lot of those values there one by one, or you can directly put it here at the beginning of this. You don't have to put it at the beginning. Beginning will make things easier. So let's try this approach first, maybe. So we're going to put what are we putting there? Yeah, we're putting the address of OS there, right? Address of OS. And we put many of that there. And then here we just put a no. So how do we refer to that?
And someplace we will see that same address printed out, right?
Then we still need we needed the address. We needed the address that out of this place, right? Yes, we will need the address of that here.
That you would have actually taken from somewhere. So you have to. I would have put it
Yes,
the ten from. Then in the ten from we have the address.
yes. Yeah, we need the address of course. So this approach actually doesn't work because this where we need the difference twice. Yeah. So we put the. Okay, so let's try this. So this is 5. Okay. So we put the address of OS at the beginning, 0804 C034. Then after that, we will have %x to read the stack. It will print out the stack. It will first print out those characters may not be printable. But after that, it will be %x. So let's put maybe several percentage x0 and makes each of them 8 bytes. So we can really see them. And let's try this first. Okay, so it is print out. So we do not get any byte of those. So maybe, so those are very small or big numbers. So maybe none of them is printable. Verify that. ASCII table. ASCII table. The value we have is 0.8. So this one is backspace, not printable. Then another 0.4. Yeah, another 0.4, obviously not printable. End of transmission. Then we have C0. C0. So C0 is even higher than 7.4. 7F, so not printable, but this one a little bit tricky. 34, is 34 printable? 34 is actually, looks like 34 is printable. Hex 34. 34 should be a 4. Okay, so why we didn't see a 4 here?
I don't know.
But at the beginning, we should say a 4 somewhere here, right? Let me first print out this. Even this one, there is no 4. Why? So here we say a 4. There is actually a 4, but somehow when we print it here, it's not showing. Yes, but I'm trying to figure out why this 4 is not showing. This 4 is not showing here. It's actually not important. I'm just trying to understand why this 4 is not showing. Okay, all right. It is. Yeah, it's just the number 4. Yeah. It's letter 4, yeah. Yeah, it doesn't really matter. So let's forget about that. Figure out that later. So we add more of this percentage 0.8x. Oops. We type this into program, and we are trying to find the address.
I got the address and the
7, okay. So we're looking for this one, right? So let's add a little bit more. So right now we have 4 of those. And so now we have 8 of those. So now we actually find it here. Okay. So what is the values here? Say there's a 0 here. Trying to figure out what this is. There should be a return address somewhere.
That's the.
Yes, I'm trying to understand each of this. What are those? Yeah. So this looks like the saved EVP, maybe saved EVP of printf itself. So this could be the return address of printf, which is in the main function. So let's say this is about to, yeah. So this one, yeah, in the middle of all 29, 329. So let's say where Volvo is just from here. So Volvo is, say Volvo is at 9316. Volvo is at 9316. So the address we have here is 9329. So that is in Volvo. Okay, so this is printf's saved EBP, printf's return address out of Volvo. Then from here to here, there are just some local variables in Volvo. We don't really know how many they are. Also, the compiler may do something we don't know. That's why we put some percentage X here to skip those. And eventually we find this one. And this is what we put in the temp buffer at the beginning of temp buffer. So at C code level, from here to this, that's actually a C string. But printf is interpreting those as integers, 4-byte integers. And this is the first 4-byte integer. This is the second 4-byte integer, which is actually what we have here is the percentage. The percentage sign is 25. That's why we get 25. Then 0. 0 is 30. And 8 is 38. X, the lowercase x is 78. So this part actually maps to these 4 bytes. Then the next one will be adult. Adult is, what is adult? 20 is white space. Whatever, right? Okay. So now what we need to do is this number corresponds to this number. We don't really care. What we care is about this number. Okay. And this number, we're changing it to what? We're just changing to percentage n. This one, instead of percentage 8, we have percentage n. Okay. Then we are going to write some value into os. Okay. Make sense? But what is the value we write os in this case?
Number of bytes.
Yeah, how many? So here we have 4 bytes. This is 4 bytes. Each of this is 8 because it's 0, 0, 8x. Each of this like this, 8. Then I put a dot there, so each of this is 9, right? So this is 1, 2, 3, 4, 5, 6. So it's 45 bytes, actually, 45 bytes plus another 4 bytes. That's 54. That's 58 bytes in total. So what we're actually writing to os is 58. In this case, doesn't really matter. The program doesn't care what number you write it. Okay, so that is how it works. Let me think about the other approach. This approach. Yeah, this approach will be tricky. So if we put this in environment variable, we actually can make it work. So if we put that address in environment variable, it will be somewhere there, top there, right? It will be top there, very high. So if we put enough percentage X, we figure out that value, it still works. It will be much more difficult. Yeah. Make sense? This approach should work. Good. Yeah.
I did not completely understand why changing that percentage to percentage was because
Percentage what?
we change the percentage to percent n, then it works right because of that.
So
Why?
from here to here, right? So percentage X, we're look for an integer on the stack, right? And it will print out the integer. Percentage n, so integer is 4 bytes. Percentage n, we'll look for an integer, but we'll treat that integer as an address, which is also 4 bytes. So those two, they correspond to the same value on stack, but use them differently. This one use that value of the integer, print that integer out. This one use that value of the address and try to write to that address. And that the address we have here is the old address.
But in like the printf syntax, you have to use that as manually, right? So, how is it working with it?
So this whole thing, the format string. After the format string, we didn't really give enough parameters here.
You have to get the format string in no tab.
The format string will use this, the printf function will use the format string to look for the parameters. Yes, yes, because at compile time, you don't really know how many parameters are there in this case, because this is variable argument function. Yeah. Make sense?
Combine that if you have more number of formats like
You will compile. The compiler doesn't care. The compiler will only treat the format string as a C string. It's at the runtime you will check how many parameters are there. Yeah. So in this case, the number of parameter will be the same as the number of percentage sign. And in the average function I showed you last week, the number of parameter is defined as the first argument, an integer there. There are many different ways to implement this. How do I know? So that's why we were doing percentage X first. So we try to print out that value first. We print so many values out, then we figure out the 1, 2, 3, 4, 5, 6, 7. The seventh parameter, the seventh value is the value we put there, the address of OS. That's what we put there, right? We put the address of OS. This is how we put it there. And in the beginning 4 bytes, we put the address there. And we're looking for the relative distance from printf saved EBP or return address to that address. So after we figure out is the seventh, we change that the seventh to n. We do not change others. If we do change others, it doesn't work, right? Let's say. So this one go back to X. This one we change to n. So this is the 1, 2. This is the second. What is the second? Second one is actually this one. This is the first one, second one. 1, 2, 3, 4, 5, 6, 7. Right? So now we change the second to n. Then we are going to write some value to this address. And what is this address? That's the saved EBP of Volfu. So we're going to overwrite the saved EBP of Volfu. So by doing that, eventually we will trigger a segmentation fault, obviously. That's that one. We're not triggering segmentation fault here. First one. This one, this one, this one. So that will be voltage. So eventually we should trigger a segmentation. So the third one we do trigger one. So this address we trigger a segmentation point. Oh. All of them should trigger segmentation. So third one, they could trigger one. This one is not showing segmentation fault, but let's say. So what is the command to get the return value? Question mark, right? Yeah. The question mark here is error. Oh. We are writing something. Yeah, we are writing something. We're writing to. But going to this one's missing. Yeah.
But it's again there, so it's not-
Yes, exactly. Yeah. So we are writing that. So when we overwrite that, the writing itself will not trigger segmentation fault because it's on stack, it's writable. But that location is supposed to be. That location is supposed to be the.
Why put it in the main view? I mean. We are already.
Oh. Let's say. No. So this one. Will call Volfu will return. When Volfu returns, it will return to main and it will use that saved EVP. So it should trigger the format, trigger the segmentation for. I'm not sure yet, but the second part, but this one, if we change this to percentage n, we change this to percentage n, we are writing to this address, and that address is code section. Code section is not writable, right? So because of that, this one triggers segmentation fault. Okay, let's debug this one to figure out why this might not trigger segmentation fault. What purpose? This better?
Yeah, I just played the. I just played it.
No, that's
For one entity. Yeah, but that's the back that we do.
so. This is the return address on the Volfu stack frame. This is a safety EVP. This is actually a local variable on printf. Yes. That's a local variable. Yeah, we don't know what that value is. It's a local variable. So now we are trying to figure out why we override here. We didn't trigger a segmentation fault. So it could be another fault and it's not showing there. So let's try to debug this. Which one is it? Second one, right? This one. We are going to GDB this. And we are going to do this one. Copy this part. Put there. So we are going to run this one. $3 sign. Okay. Okay. We set a breakpoint and Volfu. We run this program with that input. Let's see. First to verify that address. So we are already involved. So if we print PHP, we exam for big values and ESP. How do I do 4 bytes again? What?
Or
B? That will be 5. No. Each one I wanted to be 4 bytes. It's not G, so G is 8 bytes. Whatever command to do that. What? Not G.
We don't make it would be
Would be there? No. It will be just bytes. Viewers? No. That's decimal. It's decimal. Yeah. So, now we can look at G. This word show 8 bytes.
but I'm doing for what.
What? Oh, W, yes. W. Okay, cool. Okay, so we are at the beginning of Volfu. So better go back to ETP. So we're out. We're at this place. The very first instruction of Volfu. So we are supposed we're pointing at, because I also add assembly here. So it's a little bit tricky here. So this one is probably looks like yeah, but not that's not the value 0. That 0 is just a placeholder for that stack variable stack. Yeah. So this is the stack. This is we have multiple. Which one is this? We have multiple. We are at a multiple. Okay. Okay, so now we are at Volfu. We are at the beginning of Volfu. This is what EBP looks like. We respect our instructions. We're not doing that yet. Okay. Now, right now, so after EBP, after Volfu set up the stack, it should look like this. Right. This is correct. This is the saved EBP, right? FF something stack address. Then this is a code address. This is main. Okay. And the address of this, I think we're overwriting this one. So this, look at this address, B678. That probably is what we were trying to overwrite before. B678. No, we were trying to override this address. Oh. So we were trying to override this address, F7FB. This is not. Oh, okay. You see, when we run this one, this print out the return address of Volfu, which is a FFFFP68C. So the return address, the saved EBP for Volfu will be a little bit lower than this, 4 bytes lower than this, right? Yeah. So this value we get here is not the saved, is not the saved EBP value. Okay. So then what is this address? this is a return address. Oh, okay, okay. So this is the saved EP address of printf. Okay. That should be. So we have main at the beginning, main calls valve calls printf, right? Then that is printf. Printf have this saved EBP, which is F7, FB 9588. And the valve calls that. Then it has a return address, which is 80, 49, 39, 29. So this is part of 39, 29. That is part of valve. Yes, 39, 29 is part of valve. No, 39. This is 93. Oh, hang on. Is it 39? Did I read that correctly? Oh, 93. 93, that's correct. Okay. So this one is 93, 29. Okay.
But why printer returning to the after like at that instant? Printer should return is lower rate. So that was after.
Yeah, I'm trying to figure that part out. Let's read this. 93, 29 for sure here. And this is part of hold on. This is in print. So printf is printing out that for us. So this is not printf's. This looks like a garbage on the stack. Maybe is there other function before? Oh, okay. I think that could be the garbage from fgets. Okay. So we have printf. We have some percentage x there, right? Each percentage x will look for a parameter. And the parameter is above the return address and the same EBP of printf. Make sense? Yeah. So whatever we print out here is not on the stack frame of printf. It's actually we're printing out some local variables in valve. Okay. Some local variable, but they're not really local variable in this case. I think those are the value left by. So before that, we are making another function called gets, and gets will make a lot of other function calls, of course, and they are going to use that space. So eventually, when we call printf, those values were left there because no one cleans up that. But those values are not the value of the printf stack frame. So those values are not used anymore. That's why even if we override this part, it doesn't trigger a segmentation fault because no one is using whatever is at that address anymore. Okay. So to debug this, we should maybe go to fgets to say who put the value there. Yeah. Go ahead.
Using that is the local variable of
Basically, whatever is above printf factoring, it will start looking for the.
Yes.
But why is it?
Because it's looking for, so printf, the first parameter. What is the first parameter? The format string, right? The address of format string actually. Then, but that parameter already has an address higher than the return address and saved EBP already. Then you look for the next argument, which will be higher than that. So you were not print out the stack frame of printf itself. You are printing out some values higher than the address. But in this case, those values, those addresses, those values, they do not have they're not useful anymore. They are there because the previous function calls this printf and also whatever this printf calls to, this f gets, and whatever this f gets called to, leave some values there. Okay.
Even if I have like the parameter, it will go down and it will eventually find the return address for that.
No. If we put a lot of percentage x there, eventually we will find the return address of volatile, not printf itself. Yes. Make sense? Okay. Make sense there? Okay. So that's why that address is not the saved EVP of printf. So if that address is a saved EVP of multiple, it definitely triggers segmentation port. So this one, at this point, I don't know what that address is. At a much lower location. So first of all, look at the number. This number is F7FB. So it's probably still on stack, right? I think a possible explanation, but that's a very small number compared to FF. That's very low. That's very low. Yeah, compared to FF, it's very low. Yeah. We can take a look what that address is. So first of all, we can just examine that address. What is that? F7. Can someone read that to me? F7FB. Like this. So first of all, it's readable, right? When we read this, doesn't give us a segmentation fault. I think I can directly write this. Does GDB support this syntax? No, doesn't support this. There's a way to do this. I don't remember. Set or something? Set. That's the address. Error? This? No. Oh no, those are set architectures, not set values. Okay, anyway, so that is a readable address. It's very likely to be writable as well. It's a info files. You can find that. It's F9, F7, F7, F9, F7, FB. Okay, it's somewhere here.
It's UPPL. UP.pl.
This one. Okay. Oh, this one. Okay. Yeah, so this place should be writable. Oh, it's actually here. Okay, this one. Yeah. So it's part of the libc. We talked about this. Actually, next class, we're going to override somewhere here. At this location, there are a lot of function pointers. So we're going to use format string to override this place. So when those function pointers is dereferenced, which means we're going to execute that, then we can take control. But in this case, we probably successfully override some entries in this table, but we didn't really dereference that. Okay, that's why it didn't trigger a segmentation fault here. Okay. The value between our buffer and the first argument is what we're seeing. Right? The
Yes.
180, the
Yes,
further distance thing.
yes,
What are the other values?
yes.
So they are. Who puts them there?
The compiler puts them there. And at the runtime, the reason we use %x there is we do not know how far they are away from each other, right? Because compiler can do something and the runtime it can also do something. When you see a lot of functions at the very beginning, they have subtract some value to reserve space for local variables. But at a runtime, there can also be functions to do that. I think it's kind of analog. There's a C library function called analog. The ALLOC. Yeah, I think it is function. So it's not malloc, it's analog. In malloc, you're going to get a value from heap. Yeah, but in using analog, okay, I remember put analog. It's analog car. Okay. Yeah, it's analog car. There's an A there. So this function where this function analog car, there's an A. Okay. This function will actually allocate space on stack instead of heap. So when this is translated to instructions, assembly code, it will just subtract some value from ESP further. Okay. This is runtime because you can have a for loop to decide how many times you want to do this, right? That's why it's impossible to tell the difference, the size difference, because between this printf and lawful, there are many functions called here. There's another printf, and that calls many library functions. There's an fgets, calls many functions. So you don't really know what happens there. And we don't care about what happens there. We only care about it at this point,
Why does the compiler subtract from ESP before pushing argument? Does like push not do it by default? When you push something, ESP subtract it, right?
So at the beginning of function, we have a subtract. That is to reserve some local variables. And those local variables will be referenced using a relative address to EBP. Yeah.
But if you're pushing, you put a call. That if you don't need to get it back.
You don't, because the push itself will subtract. Yes.
Maybe the optimated.
Yes, so those instructions are most likely for local variables and also for alignment. Sometimes compiler makes alignment for better performance. Yeah. And sometimes you say there are two subtract. After one, there is another one, and you were thinking this doesn't make sense. That's just the optimization. Yeah. Yeah. You can generate a better code than that. Okay. What time is it? So we still have. So we have tier 125 something? Okay. Let's see if we can do one more. So now we understand this one, and we understand why they doesn't trigger the segmentation for. Okay. This one is very similar. But we're overriding two global variables, os and os1. And we're overriding with a very specific value here. The first one is 60. The second one will be 80. And we're going to do this in two ways. But first, override os, so it's then OS1, then we override OS1, then we override all. Okay. So you already know, and I print out the answer for you to make sense easier. So this one actually at the beginning it will be easy, but the second part will be a little tricky. So, 4 mark string 6. Let's try to finish this one. 4 mark string 6. So there is a local buffer, 512 bytes. F gets into that, the low buffer overflow, we're using that as a format string. So there's buffer, so there is a format string vulnerability. However, this one doesn't trigger buffer overflow either. But we're going to override this. So the idea here is to exploit will look like, so first is the address of OS, right? Then the address of OS1. That's our exploit. Now after that, we will have some percentage X. We will have some percentage X. Eventually, we will have 2% N here, right? Make sense? 2% N. And we need to make sure that the first percentage X, before that, we print out 60 bytes. The second percentage N should be 80 bytes, which means between this percentage X and percentage N, we need to add something. Make sure it's 20 bytes. So maybe we'll put a percentage X or D, whatever. Maybe percentage 20X, then percentage N. That makes sense? Yeah. And even the first one would maybe give you an integer overflow and something. Yeah, okay. Let's see. So 4 mark string 6. So we will first run this program. It gave us, oh, it only gave us a value. It doesn't give us the address. We still need to figure out the address. So no matter how many bytes we put here, it will not trigger the. We do an NM here. So those are the two addresses. Copy one of those. And X, X, X. We do not see the value yet. More percentage X. Oh, we see the value here. So we put two values. One is 34 is 38. We put that value 3430 for there. Then we put percentage X here. So now we find the fourth. 104. This one. It's what we want. Okay. So we change that to N. So this now the OS should change. Okay, OS now change to 25. So the real value we want here is what? We want the 60. Okay. So how do we get 60 from there? What? Yeah, we just need to put 35 in any of those X there. And it's not enough. 42. Yes.
Why did that not work like it happened with me also? When you put 35, it's getting 50 now.
You need to count. How many are there?
But before that, it was 25.
Before, this one is 25, right? Which means from here to here is 25. So I didn't put 0.8 here. First of all, I didn't put 0.8 here. So for example, this one is not printing out 8 bytes. This one is only printing out 3 bytes. Yeah. So basically, here we have 4 bytes, 4 bytes. And this X only 3 bytes. That's 7, 8. This one does give us 9. That's 17 something. This one another. Yeah, this one is another 9. That's why we get 25, 26. Yeah. Go ahead.
I guess I think I'm also confused here is that if the first count said 25
Yes.
and then we put 35 more characters in, then it reads 53 is that's where I'm confused.
No, because this one already 8.
Yes.
Then
Okay.
you put 35 there,
Okay.
you're adding 28.
That makes sense.
Yes.
Perfect.
Cool. So this one we need to put up. Oh, we need to put another value here. 38. Say 0. Zero 8. Oh, 0. Here we put 4 more bytes here, so here we need a -4. 38 should be right. Then we have percentage n. Then between that we need another 20 bytes, but I have 2 dots there, right? So it should be 18, I think. Yeah, 18. Then percentage, let's say correct. It's not. Oh yeah. Why this is not correct?
Both of the address is like.
Okay.
So how can we ask them to use it?
Exactly. So this percentage X is going to use this address. Right. So this percentage N will actually use this. So we need to put 4 bytes of garbage in between those 2 addresses here. We're gonna do that.
Or we can just use the regular character.
Yes, you can do that. So then you need 20 bytes here, right? Let's do that. Yes, that should work. Yes, one way to do that. Another way to do this is, like I said, we want to do percentage X 18. 18 would be good. Dot. Then here we put 4 more bytes, but because of this one is -4 again. Okay. Going to this also works. I think we can stop here today. We're running out of time. So Thursday, what we're going to do is, in this case, we have a small number here. So 60, 80. We only need to print out 60, 80 bytes to get what we want. What if the value is huge? That's what I'm going to do next week, Thursday. So the next example is overwrite the return address, but after that, we're going to do this. Okay. We have a huge number, okay, 3 huge numbers. So to print out those huge numbers may take a very long time. Yeah, those are, if it's FF, it could be almost 4 billion. 4 billion characters you need to print out to the terminal. If it doesn't crash, it will take a long time. So how do we do that? We can, instead of override 4 bytes, we can override 1 byte after 1 byte. Okay. So if we override 1 byte, then each of them will be just 256. But there's another thing is, if you already override, let's say 100 bytes, you already output 100 characters, then you are going to override the value 100. But the next value you are going to write will be a small value, just 2 or 3 or 50. So how do you do that? We can do an integer overflow actually. So we are going to use the integer overflow to do that. Okay, so we are going to do that Thursday. Then also maybe Thursday or next week. Yeah, next week, we will override other places. Now we have a very, very powerful vulnerability that we can override anywhere in the address space. When we do buffer overflow, we don't have such a powerful attack tool. When we buffer overflow, we can only override the return address on stack, sequential override. Now we can write anywhere. Then we are going to override the code pointers. There are so many different code pointers in the address space. Function pointers. C++, they have constructors, destructors. C program, they also have destructors. The global offset table, we're going to override those places. As long as those functions eventually get called, we can take control. So that's what we're going to do next. Okay, cool. Let me talk about the homework a little bit. So this week's homework. So this week's homework, we will turn on address space layout randomization. This is actually the materials we studied before the midterm. It were several tasks about ASLR and how to bypass that. The easy one to bypass that. I demoed that in class. Then there is the firewall, the system called firewall, the SIGCOMM. After that, there are 2 challenges for share-code development, but only one is required. In a share-code development, you need to watch the video, the one right before the midterm about share-code. This one could take some time. So start early, and I'll just ping you when you need office hours. There is a bonus point for the 64-bit version of the share-code. The share-code you are developing, the requirement is you can only use ASCII characters. There are exceptions actually. So ASCII characters are from 0 or from 1 to 7F. But I do give you an exception. You can use C0. Basically, you can use system call. You can use interrupt. Then you cannot use other bytes. Okay. It's possible to do this without even use the interrupt bytes, the int bytes. It's possible, but it's much harder. So the share code will need to make system calls, right? Which means eventually you need that int something, int 80 there. You need those 2 bytes. I think int is C0, 80 is just 80, but they are not ASCII characters. They are after 7F. You will need those characters. So the trick to do that is your share code needs to rebuild those 2 characters in memory, then eventually execute that. But it will make things much, much harder. Okay. So you can use those. Then others, basically, if there is an instruction, let's say that instruction's value is CADC, you have to find an equivalent instruction. Do not use those 2 bytes. Instead, use bytes from 0 to 7F to do that. Yeah. You can use those online disassembly tools. You can try you can sync different instructions. And to say what is the machine code of that, try different ones, yeah. So how many of you have already watched that video, the share code one? Okay, okay. So then you remember that I give you guys an example of the DNA one. Yeah, the DNA ones, they can only use CGAT, yeah, 4 characters to build to build a share code. Not only that, not every CGAT string can be censored. What is that called? Can be made of DNA basically. It will not be reliable. So there are much more. There are also constraints from the biological world. So that's a very interesting project. Yeah. Okay, so that's it. Okay, then see you guys Thursday.